let's take a look at characteristics of waves. And I'm going to draw two diagrams, and in each diagram I'm going to include two elements. I'm going to include rays and wavefronts. The rays are arrows which indicate the direction that the wave is moving. The wavefronts are surfaces which show the same part of the wave at different locations. And when I say the same part of the wave, I mean the wavefronts could show where all of the peaks are, or it could show where all of the troughs are. It's showing points which are all in phase. So in this diagram with the circles, notice that the arrows are all pointing away from the center. So that means that the waves are traveling away from the center. The center is where the disturbance is. That's the source of the disturbance. And the waves are traveling away from that. So perhaps there's like a cat poking at the surface of the water at the center, and the waves travel away from that disturbance, and the arrows are pointing away. In the second diagram, the ray is pointing to the right. So all of the waves are moving to the right in this diagram. The wavefronts show similar parts of the wave in different locations. So in the upper diagram, it could be that the wavefronts all represent the locations of the crests of the waves. So each wavefront is showing where the high point in the wave is. And in the lower one, it could be that the wavefronts perhaps represent the troughs of the waves. So we have troughs that are lined up as you see in the diagram. Now notice that rays and wavefronts are always perpendicular to each other. And that is always true. A ray and a wavefront are always perpendicular to each other at a certain location. Also, the distance between the wavefronts is always a wavelength. So, if you look at a diagram of wavefronts, to find the wavelength, you just look at the distance between the wavefronts. Okay, now let's shift gears to energy and some associated quantities. Turns out that the energy that's transferred by a wave is proportional to its amplitude squared. Okay, the energy transferred by a wave is proportional to its amplitude squared. So what that means is, if you double the amplitude of a wave, the energy in that wave is quadrupled. 2 squared is 4, so the energy is quadrupled. If you have, say, 1/3 the amplitude of the wave, then you would only have 1/9 the energy in that wave. Now we've seen power before. Power is the energy transferred divided by the time that it takes to transfer that energy. So, it makes sense that the power transmitted by a wave is equal to the energy transferred by the wave divided by time. Okay. There's also a quantity called intensity. Intensity is the power transmitted by the wave per area. So intensity is equal to power divided by the area. And let's apply that to a specific situation. Let's say that we have a source of a wave that's a single point. So the single point is emitting waves, and the waves travel out in every direction. So let's imagine that we have a shell, a sphere, around that point source. And let's say that that sphere has a radius of r. Now, all of the waves that are coming from that point source have to pass through that shell. They have to pass through the surface of that sphere. So all of the power from the source is traveling through that sphere. And the area of the sphere is 4 pi r squared. That's just the area of any sphere. And we said that its radius was r, so 4 pi r squared. That allows us to write down an equation for the intensity. The intensity on the surface of that sphere would equal the power that's coming from the source divided by 4 pi r squared. So the intensity from a point source is equal to P divided by 4 pi r squared. And if we look at that equation, we can get the units of intensity. The units of intensity then are the units of power, watts, divided by the units of r squared, which is meters squared. So the units of intensity are watts per square meter. And let's look at that through an example. Let's imagine that we have a 60-watt light bulb. And that 60-watt light bulb will act as a point source. It's giving off 60 watts. Now, if I am 2 meters away from a 60-watt light bulb, I can figure out the intensity of light at my location. So if I'm standing 2 meters away, well, I can use this equation. I have 60 watts and divide by 4 pi r squared. If I'm 2 meters away, then the intensity of light at my location is 1.19 watts per square meter. If I am twice as far away, if I'm 4 meters away from the source, then the intensity at my location is 0.298 watts per square meter. And if I am 8 meters away, then the intensity at my location is 0.0746 watts per square meter. So you'll notice, as I move away from the point source, my intensity goes down very quickly. In fact, if you look at this equation, I equals P over 4 pi r squared, if I double r, my intensity goes down by 1/4. The intensity is proportional to 1 over r squared. Now let's take a look at superposition. So say you have two disturbances, and those disturbances are both sending out waves. Well, at some location that's between them, the waves will overlap. The waves from one disturbance and the waves from the other disturbance will meet at a point. Superposition explains what happens at that point with those two waves. When waves overlap like that, the total displacement at a location is equal to the sum of the displacements from each of the waves. So, for instance, if you had two waves that looked like this, one wave like a big sine wave, and then the other wave like a smaller upside down sine wave, the total wave would be the sum of those two. So you'd get a somewhat smaller wave. Or let's look at it a different way. Let's say I had two waves that overlap. One looks like a box that's on the positive side, and one looks like a triangle that's on the negative side like this. Well, the total wave, when you add them together using the principle of superposition, would look like this. You have the box plus the upside down triangle, and you get something that looks like that. Let's look at a third example. Let's say that at a certain location, my displacement looks like this from one wave, and the displacement looks like this from the other wave. Well, the total displacement caused by those two waves when they overlap would look like this. The last thing we'll look at is polarization. Now, polarization is a phenomenon which only works for transverse waves. It does not apply to longitudinal waves, and it's usually applied to electromagnetic waves, which, remember, are a type of transverse wave. So polarization refers to the direction which the medium oscillates in a wave. So let's say that we had a wave that's oscillating up and down, and it's traveling to the right. Well, now let's imagine that we have what's called a filter, a polarization filter, and I'm going to draw it like this. And you can imagine it as similar to slats in a fence or posts on a fence. So this filter, if the wave is oscillating up and down, and the filter is arranged up and down, well, the filter will allow it through. The wave will pass through it just fine. But now let's imagine that the polarization filter is at 90 degrees to that. So the polarization filter is side to side, but the wave is oscillating up and down. Well, that filter will not allow the wave to come through. When the filter is in the same direction as the oscillation, it's fine. The oscillation is able to pass through the filter. But when the filter is perpendicular to the oscillation of the wave does not pass through it. The wave is stopped. And we can also draw this a different way. Let's imagine that we have a wave that's oscillating side to side, but we have a filter that's arranged up and down. Well, that filter would not allow the wave to pass through it. But now let's imagine a slightly different scenario. Let's say that we have a filter that's arranged up and down, but now the wave is going to oscillate not up and down and not side to side, but at an angle. If we do that, then some of the wave will pass through. It turns out that the part of the wave that is parallel to the filter will pass through. So some of the wave gets through, some of the wave does not. This is governed by an equation called Malus Law. Malus Law says that I is equal to I naught cosine squared theta. And we have to be very specific about what these things mean. The I represents the intensity of the wave coming out of the filter. I0 represents the intensity of the wave going into the filter. And theta is the angle between the direction of oscillation of the wave and the direction of the filter. So let's just make sure that that makes sense. If the direction of oscillation of the wave and the direction of the filter are the same, then theta is equal to 0, and cosine squared theta is equal to 1. So the intensity out of the filter is equal to the intensity that went into the filter. The entire wave passes through when theta equals 0. Well, now let's think of a situation where the direction of oscillation is perpendicular to the direction of the filter. Well, there theta is equal to 90 degrees. Cosine of 90 degrees is 0, so cosine squared of 90 degrees is also 0. So the intensity out of the filter is 0. None of the wave passes through the filter. Okay. There is also something called unpolarized waves. Unpolarized waves means that the waves are oscillating in all different directions. They're not just oscillating up and down. They're not just oscillating left and right or at an angle. They're oscillating in all different directions. This is important because most electromagnetic waves that we receive from sources are unpolarized. It turns out, we're not going to do the math, but it turns out that if unpolarized light passes through a filter, then the intensity of the light that comes out of the filter is equal to the intensity that went in divided by 2. So only half of the intensity of unpolarized light gets through the filter. And when it passes through the filter, only the part parallel to the filter will come through. Now let's take a look at a couple examples. In the first example, let's send in unpolarized light, and it'll pass through two polarizers. The first polarizer is oriented vertically, and the second polarizer is oriented 60 degrees from vertical. And I want to know how much intensity comes out at the end. Alright, so the key is to take it piece by piece, go through each polarizer one by one. So we started out with unpolarized light, with an intensity of I0. It goes through the first polarizer. Well, if unpolarized light goes through a polarizer, only half the intensity makes through. So, after it goes to the first polarizer, we have half the intensity of light, 1/2 I0. Also, after it passes through that first polarizer, it's vertically polarized now. Okay, so now we're going to have that go through the second polarizer. We have vertically polarized light now with an intensity of 1/2 I0. To figure out how much light passes through the second one, we have to use Malus Law. So I will equal 1/2 I0, that's the incoming intensity, times cosine squared of 60 degrees, right? Because 60 degrees is the angle between the polarization of the light that's going in and the angle of the filter. So if we work that out, the intensity that comes out at the end is 1/8 I0. And also, that light that comes out at the end is oriented, or is polarized at 60 degrees from vertical. Okay. Let's look at a second example. Let's say that we have unpolarized light, and it goes through a vertically oriented polarizer, and then it's going to go through a horizontally oriented polarizer. And I want to know how much intensity comes out at the end. Well, again, you take it step by step. So, unpolarized light goes through the first filter. Okay. Unpolarized light going through the first filter, only 1/2 the intensity will come out. And when it comes out of that filter, it's going to be vertically polarized light. So we're going to have vertically polarized light going into the second filter. Well, vertically polarized light going through a horizontal filter, well now the angle between the incoming light and the filter is 90 degrees. If we use Malus Law here, I is equal to 1/2 of I0 times cosine squared 90 degrees, which is equal to 0. So in this situation, no light comes out of the second filter.